Welcome back to Odds Learning. In this video, we'll be going over the hardest energy conservation problems that I could build. Okay? I'll be, as always, picking a select few that I've deemed were the hardest, and we'll be going over those. But you can feel free to explore the others in your own free time. Okay? My PDFs are at oddslearning.com, which I'll link in the description below. So let's get started. A 15 kg dog on a skateboard, okay? So only the dog has mass, the skateboard doesn't have mass. Let's assume that. That's not true in general, but let's assume that for right now. Starts from rest at the top of a 5-meter ramp, inclined at 25 degrees, with mu1 is equal to 0.12. At the bottom, it rolls onto a flat, rough patch, 4 meters long, with mu2 is equal to 0.3. So this rough patch. So they both have different coefficients of friction because they're different surfaces. Then strikes a spring, K is equal to 900 Newton per meter, and we need to find the maximum compression of the spring. Okay, so let me write out our equation here. It's kinetic energy initial, so work non-conservative, plus kinetic energy initial, plus potential energy initial, plus energy spring initial is equal to kinetic energy final, plus potential energy final, plus energy spring final. Okay, so potential energy, what initial values do we have here? Kinetic, yes. Kinetic we don't have. We're going to have it, but we don't have it initially. Energy spring we don't have. And what we're going to do here is, because we have two places, right? The energy here is going to distribute differently. So we can't just assume this is our starting point and this is our ending point. Otherwise, we'll have some errors in our answer. I'm going to take this as our final point, okay? Because that's when the friction surface changes, and then I can write a new equation for it. But right now, we can take from here to here, because I have only one surface there, right? So this is my initial, and this is my final for now. And that means we don't have any potential energy here because we don't come there. I mean, we do come there, but its height is 0, right? So we don't have energy spring final. That's over here, but what I tell you, we'll consider this as our final, right? Because we have to get through this patch of friction as well. So we don't have that either. So work non-conservative plus potential energy initial is equal to kinetic energy final. So what is our work non-conservative going to be here? That's going to be mu, right, times mg. Is that our normal force, or do we have something else? Since it's on a ramp, remember when I explained how mg points straight down, mg sine theta is here, mg cosine theta is here, and we need to get it to balance across, right? So it's n mg cosine theta. And then what? We have that. But that's only our force of friction. We need to multiply it by our distance to get our work done by friction, right? How long is this board? That's around 5 meters. 5 meters. And then since it's over here, it's a negative value, right? Because we're starting off with this. This energy isn't going to be included in our final energy. Potential energy initial is plus mg. But what's our height here? Do you have our height? We don't have that, right? We have only this ramp's length, which is 5 meters. How can we find the height? So sine of 25 of this block here is opposite over 5, right? So opposite is equal to 5 times sine of 25. Okay, so 5 times sine 25. And then all of that is equal to our kinetic energy final. Now the reason I'm not writing this as 1/2 mv final squared is because we don't need that, right? We just need to know how much energy it has at this point. Once we know that, we can use that energy initial over here. We don't really need this actually, right? So we can ignore it. So then this would be negative mu, or so what's that going to be? Here, negative 0.12, right? Because that's mu1 for this ramp, times m, 15, times g, 9.8, times cosine of 25, times 5, plus 15 kgs, times 9.8, times 5, times sine 25. And that's equal to our kinetic energy final. So it's very, very intricate, right? If you even mess up one term, you could possibly screw up the entire equation. That's why I wrote it all out before I started solving, right? So then I know what to plug in each time. It's a very useful tactic. You want to make sure, because these energy problems, they get very messy very soon. So negative 0.12, okay, times 15 times 9.8 times cosine 25 times 5, about negative 80, and then you add 15 times, so 15 times 9.8 times 5 times sine 25, and then you should get about 230, I believe. Yeah, 230 point, I always round to the 2 digits, okay? It's just a habit, so that's what I'm going to round to here. 230.69 joules. Okay, so this is what our energy here, initial, is. And this is going to be equal to our kinetic energy final. So then we start the second step, okay? Over here, we have 230.69 joules. So now this is our initial point, okay? This is where we start. Then where's our final? At this spring over here. Final. So what energy do we have initially? Kinetic energy, right? Kinetic energy initial, which is this value, because that's the energy we have at the end of this ramp, right? And then we have no potential energy, no spring energy. So I'm going to cancel those out. Energy spring, we don't have that. But we do have work non-conservative, right? Because of this friction here. Is equal to, what do I end with? Or my spring final. My kinetic energy, when I hit the spring, becomes 0, right? Because I squeeze it and then I stop there. So my kinetic energy final is 0. My potential energy, I'm already at the blocks. I mean, I'm already at 0 height. So potential energy is also 0. But I have energy spring final. So this is going to give me kinetic energy initial, which is 1/2 m. Or we could just, what am I doing? We could just plug this in, right? 230.69 joules. Plus, what is our work non-conservative going to be? Same thing, mu times m times g. Do we need a cosine? Well, when the block's here, the mg is the only thing pulling it down, right? To keep it upwards, the normal force just needs to match that, not a cosine. Because over here, the angle was different. But here, it's just flat ground. So mu times mg, okay? And then what? So this is our work non-conservative, mu times m times g, no cosine theta. But what else do we have? We have to have this is our force of friction, but we need our distance, right? How far do we travel? 4 meters. Times 4 meters is equal to our 1/2 kh squared. Now the reason I did that and didn't put it as energy spring final was because we need to find out how much it compresses, right? See compression of the spring here? So that's how we're going to do that. We're going to need to know 1/2 kh squared, right? We're going to need to solve for the eths here. So if you continue solving this, you should get 230.69, right? So I'm just going to scroll a bit up because I don't have much space here. Plus mu, which is our new mu of 0.3, times m, which is our mass, right? 15 kgs, times 9.8, times 4, and then the whole thing times 2 is equal to kh squared. And I can replace this K with our spring constant, right? Because we know that, which should be around 900. Okay, so what can I do then? I can divide this entire thing by 900. So let's do this. Okay, this is going to be a bit messy. So 2 times 230.69 plus 0.3 times 15 times 9.8 times 4. That divided by 900 and then square root of that. So it should be around, should end up getting about, so let's see, that divided by 900, okay, 0.9-ish. And then you want to put the negative here, right? Always remember the negative. So that's why my answer looked a bit off. I mean, I put the negative in my answer, but I was just looking at what I wrote down here, and it was a bit confusing. So negative here, right? Because this is working in the other direction. That means your final force is going to be lesser because friction is taking some of that initial energy you have, right? It's turning it into heat or sound or whatever, right? So then you're going to have about 0.347 meters. And that's going to be your compression of spring. So it got very messy, Now, we're going to proceed to question number 12, okay? So here, we have a 5 kg block on a 30-degree incline. Mu is equal to 0.2. It's joined by rope over a pulley at the apex to a 9 kg mass hanging freely, as shown here. Released from rest, find the speed after the hanging mass descends. Height is equal to 1.2 meters. It descends that much. Okay, so imagine the block started here and it descended that much. Or it could have started here, but that's fine, okay? So let's write our equation first. Work non-conservative plus kinetic energy initial plus potential energy initial plus energy spring initial is equal to kinetic energy final plus potential energy final plus energy spring final. Since we don't have any springs here, I'll cancel out both these energies. And we start from rest, so we don't have a kinetic energy initial. But so what do we have? We have a potential energy initial, which is, we have two of them, okay? We have over here, for this big mass, imagine that it started here, right? It's the big mass's potential energy would be mg times this big H, which is 1.2, but we can substitute that in later. Okay. And then what? What is the other potential energy we have? We have the potential energy of this block. Okay. Little m, g, we don't know the height here, so I'm just going to say h0. But this is going to cancel out soon, okay? Because it's the gain that's measured, but I'll just put it here for now. So that's your potential energy. What's your work non-conservative? It's force of friction times d, right? And since it's acting in the opposite direction, it's going to be a negative here. So our force of friction, which is mu times, for this block doesn't have friction. For this one, m times g, because what's the normal force? I mean, it's going straight down. This is the mg sine theta. Mg cosine theta is pulling down this way, and it's being deflected by the normal force. So it's going to be cosine 30 times d, which is how far it travels, or h, right? Because it travels 1.2 meters. If this goes down 1.2 meters, it pulls this block at a distance of 1.2 meters, so it travels that much. is equal to kinetic energy final. So both of these blocks are going to have the same same velocity, right? If they start from rest, then the whole system is going to accelerate at the same rate because they're connected. So both of them are going to have the same velocity because they start at 0, and if they both accelerate at the same pace, they'll both have the same velocity, right, accordingly. So 1/2 big M v squared plus 1/2 little m v squared. Both of them have the same velocity, so v squared will be the same, but they have different masses. Plus potential energy final. When this block hits the ground, it doesn't have any potential energy, right? Height of 0. But where do we have potential energy? Over here, right, for this block. And what's that going to be? That's going to be little m times g. So it starts at h0, which is what we determined to be the height. Then how much do we gain here? How much height do we gain? 1.2, but remember that 1.2 is just the distance we travel, right? In order to find the height we gain, which is this part over here, height, little h, we have to use the sine of 30. Okay? 1.2 times the sine of 30 will give us this opposite side. So 1.2 sine 30. So now I can just plug in, or there's a few, let me just show you what cancels out here. Big mgh plus mgh0 minus mu mg cosine 30 times h, big H, is equal to 1/2. I'm just going to factor this out and put m plus m inside the brackets, okay? Because it's a bit messy. I could simplify it, right, like this. I can just factor 1/2 v squared and get this here. Plus mgh0 plus 1.2 sine 30 mg. You can see here how there's mgh0 here and there's mgh0 here, right? So we can cancel those out, because if you subtract, it's going to cancel out accordingly. So m big M g big H minus mu mg cosine 30 times height is equal to 1/2 m big M plus mv squared. Now I can subtract this 1.2 sine 30 mg from here, right? Minus 1.2 sine 30 mg, because I want to get rid of it. I want to isolate for the velocity. So now I'm going to start plugging in here. So here this should be big M is 9 times 9.8 times height of 1.2 minus mu 0.2 times 4, because it's a little m. Sorry, 5, because it's 5, right? 5 kg block times 9.8 times cosine 30 times 1.2. Because that's, if this block falls down 1.2, it's going to move a distance of 1.2 along the ramp, right? That's how much the rope gets translated. And then from that, I'm also going to subtract 1.2 times sine 30 times little m, which is going to be 5. I keep saying 4. 5 times 9.8. So first let me compute this, and you can see how it's a lot of numbers, right? So do be careful. It's very easy to get tripped up on these. If you mess even a single number, that's it. You're probably not going to get the right answer. Okay, so these you have to be very cautious on. Always track your numbers here, track your digits, track what you're doing. Make sure you're not doing something wrong. And then you subtract the 1.2 sine 30 term here. Then times 5 times 9.8. So you get around 66.2555. Okay? Then what are you going to do with that 66.2555? You're going to multiply it by 2, right? Because we need to isolate this term here. That's going to become big M plus M v squared. So if I multiply that by 2, I should get 132.51 is equal to, this is just 9 plus 5 v squared, right? So v squared is equal to 132.51 divided by 14. And then you take the square root of that. So actually, let me take the just square root of this, right? Take the square root of this, and your velocity is 3.07. So I can just round this up to 8 meters per second. So a lot. You see how many variables you have here? You definitely need to keep track very carefully. Okay, one